Good afternoon. Now we continue our revision about probability and stochastic process, and also the classification with Bayesian. And we mentioned last lecture that we can build our like selection or clustering based on this Bayesian formula, that the probability of the class given the attributes x can be represented in this form. We explained this last lecture, but here the difference that we use probability density function instead of probability mass function as we shown before. And one reason that x here can be like continuous, so in that case we should use the probability density function of x given r. Probability of r divided by the evidence is the distribution of x. And here we call the probability of the class as a priori probability, and this is the probability of r given x is a posterior probability, because we take this probability after we know the attributes x, and this is f of x is called the evidence, and f of x given r is the likelihood. And also we this is in general the formula in general, but we showed also that we should select the class which maximize this probability. So if we have, for example, any classes, then the probability of the class Ci given the attributes x, we select the class which maximize this one. One example is for the classification of handwritten, for example. So people can, for example, write letter A in different shapes, like A or A capital, or it can be, for example, something like that or something like that or whatever. And then we have letter P and letter C and so on. Now, if we count how many classes that we have, so if we assume that we have 80 classes, contains all letters from A to Z, capital and small, and also we may have other symbols like equal to or multiplication or division or brackets and so on. So if we assume that we have 80 classes, then we have from C1 until C80. Okay. Now using this Bayesian formula, we can classify data, because in the beginning we make the training or building the likelihood function based on this like maps. So for every letter we have some maps. For example, let's say 10 by 10. So we have 100 pixels for every letter, and then so during the learning, we built this table that we have this input x, and then we have the class C. So for certain input, we have class C. For example, this is A, and this is B, and this is C, and so on, until 80 possible that class. And based on this, we can build our likelihood function, which is like, for example, probability of x given the letter or the class Ci. Okay, and also we build the priori probability of Ci. It means that the probability of each class in the data, that we have a lot of data, and for example, how many A's there, and how many C and how many B, so we can build this probability, and this should depend also on the the number or how much this every letter used in the language. Okay, and then we can for certain class or for certain reading x, we are interested to calculate the probability of a class Ci based on x. This can be done as we show. before that, in this, for example, in this formula, in the Bayesian formula, that we can calculate probability of each class based on the map that we read. And then once we compute the probabilities, we select the maximum one. For example, if the maximum was for letter B, then we decide that the class is B. So this is the Bayesian formula. And what will be the risk if you made wrong like classification? If the risk is equal, so we just select the maximum probability in this case. However, this is not always a good decision, because in some cases we might have risks based on the decision. If the risks are the same, of course we can just select the maximum. But if the risks are not the same, then we should apply or we should modify our formula a little bit. Let us start with example, simple example. That there's a doctor, okay, medical doctor, and he received one patient. He was over 60 years old, and he had a terrible chest pain. The pain based on the history in that hospital. So for this age, that the pain, most likely 50% of cases, that was because of muscle attractions in the chest. Also, this guy, he had like heavy dinner. So also 30% of cases, they were because of some colonic problem. So they made that chest pain. So it was 30% of cases or chances. Okay, and they are smaller, like probability that this guy had a heart attack, and the probability is only 15%. And many other things with minor diseases can be 5%. So now if we calculate the probability, so the probability, if we call, for example, class 1 is the case that you have just muscle pain or muscle attraction, and C2 is just because of heavy food, and C3 is heart attack, and C4 is some minor diseases. So we have now 4 classes. Now if we compute, because with these symptoms that this patient have, then if we calculate the probability, so the probability that of being within C1 given the symptoms that you have for the patient, then this probability for being with just muscle attraction is 0.5. And the probability of being in C2 given the symptoms is 0.3, and the probability of being heart attack with the symptoms is only 0.15, and the probability of some other minor reason given the symptoms is 0.05. Okay, so now if we just make our machine learning is based only on this probability, of course it will select this one. So it is just a muscle attraction, and give this patient some like painkiller like Panadol and tell him to go and relax. But is that good decision? Of course no, because the risk of being in heart attack is very large. The risk is very large. The probability is small, but the risk is very large. So in that case, that decision was wrong decision to be taken. Okay. Now for a human doctor, he knows this because he has awareness about the situation. But in machine, if we would like to make this automated, so we have to modify our equations in order to be able to take the right decision. Okay, now we will make a little bit change about the equations, that we add this risk factor. So the risk here, or the expected risk, is based on taking action I based on the symptoms, or based on the attributes that you have, is equal to the summation of the loss factor, lambda ik, I will explain what they mean, times the probability of selecting the class ck based on the attributes and we take the summation over all possible classes. What this equation means? Okay, now this loss factor, lambda ik, is a parameter, indicates that the loss, if you select or if you take action I, okay, and the actual situation was k. If you take action I, because now we have how many actions that we can take for this example? We have 4 actions that we can select, the class 1 or class 2 or class 3 or class 4. So this lambda, for example, if you take class 1, okay, and the actual situation was the same, it was also class 1. In that case, lambda 1 should be 0 because there is no loss, because you select the right action. So we don't have any loss in this case. So in general, lambda ii equal to 0. So if you take the action for the right decision or for the right case, so there is no loss. But if you take action C1 and the actual situation or the actual case was C3, so C13, it means that how much loss you will have if you take action 1, class 1, and the right action was class 3. In this case, if you ask the patient to just go and relax and he has like terrible heart attack, so he might die. So in that case, this loss can be very large number. This loss can be very large number because the losses is very high in this case. It is not necessary, of course, to take only this for patient. For example, if you are boss or you are CEO in some company and you want to take a decision based on some like information that should you invest some money in some project or not. Now, when you compute, for example, the money that you need to invest is not that much, but also the chance that you will win that project maybe is small. However, the reward, the risk is not only risks, can be also rewards, but the reward, if you get that project done, then it can be very large. So again, you can apply this formula. What is the loss if you miss that project? How much it will be? So this can be quite a very general equation in order to study the situation that you have. So in this case now, what we should compute? We should compute the risk if you take action 1, given the symptoms that you have, and when we take the summation over all possibilities, that if you take action 1 and the case was already 1, then lambda will be 0. So the first element will be 0, plus what will be the loss if you select action 1 and the actual case was 2. Not that big loss in that case. Not that big loss. So we can say it is only one loss in that case. Time is the probability. So the probability that you select 2 given the symptoms that you have, plus here we have the problem. Here we have the heart attack problem. We have the highest loss that we can have. So it is maybe 100, maybe 1,000. You can put any number to indicate how much that loss will be. Times the probability that C3 given the symptom is X, and finally plus 1 times probability that C4 given X. So in that case, you build the risk if you select action 1. Now we do it again. The risk if you select action 2. Action 2 means that you decided that you will have class 2 and given X. Then you compute again the risk if you take action 3 given X, and so on. Once you computed all risk factors for every action, you select the one which has the minimum risk. So now we change it a little bit. We was thinking about selecting the class which have the highest probability of Cx given x. Now, Ck given x. Now we change it a little bit, so we are looking for the class which minimizes the risk, In this example that we have, so it is clear that we should always select action 3, because action 3 or selecting class 3 always will have the minimum risk. So it always will have the minimum risk. Okay? Okay, now we talk about Bayesian formula in order to select the proper class, and also we have seen how to compute the risks based on that and how to select the proper action. And now we start a new topic also related to the probability concepts that we can apply for data. So one of the important application, if you have a lot of data, if you are you made a lot of data analysis or data analytics, so you have always, or you are always looking for the dependency between different items in data. For example, you are interested that is X leads to Y or not in general. Is action or attributes X always lead to Y? So in that case, we call X like antecedent and Y is the consequent of that in the data. For example, is it true that always fault X leads to fault Y? If you are working in some company, for example, technical company, and you're in maintenance, for example, is it that when X happen, is it should it lead to fault Y or not? What is the relation between them? Or if you are in some market, once Y is sold, does it affect that X was sold before or not? So it is called basket analysis in that case. What is the smoking? Large smoker, is it necessary that it will lead to, for example, diabetes or not? So now you have a lot of data. You have a lot of data, and you like to study the relation or the correlation in this data. You can do that by checking 3 elements in your data. First is called support of association. So you need to have a support for your association assumption, because now you start with some assumption. Actually, we have one master student, he did his master in the same topic for data in some company. So he starts with some assumptions that when the company requests some item, that they usually will request also that another item. So we don't know, this is hidden in data. So you have maybe sometimes like gigabytes of data, and you are looking there, is there some information you can extract. So in order to support or to guarantee the assumption is right assumption or not, we need to check 3 rules. The first rule is called support of association, and the support of association is nothing but the probability that event X and event Y happen together. Okay, so to explain how this works, I will make some simple example so we can explain over that example. Okay. Assume that we have some data, and this data indicates that the possibility for certain diesel engine to get fault, for example. So, and now we have some attributes, x1, maybe temperature, vibration, whatever. So we have some elements here, okay? And then we have the output is the engine condition after 1 year, okay? 1 means that the engine has some fault, and 0 means that it is good, and maybe also in between. So it is so it works, but it has some problems. So in that case, we say that after 1 year, the engine is out of order. So it is 1, it means that it is out of order. 0 is working fine, maybe 0.5, maybe 1, and 0, and so on. And then we have also some data. This data indicates some attributes about the engine, about the environment, about the temperature, about the weather, whatever. So we can say that, for example, it is 1, 2, 3, and here we have 1, 2, 3, and here we have 0, -1. It can be any values, of course, just we fill anything here, 0, 1, -1, and so on. Okay. Now we have a support, or we said when we have attributes 1, 2, 3, maybe we have here also 1, 2, 3, but it was working, and maybe some in the data we have 1, 2, 3, but the engine was so, okay, and so on. Now you think, or there is like general impression that when the attributes are 1, 2, 3 about the engine or about the environment, most likely after 1 year, within 1 year, this engine will be out of order. And you have a lot of data based in history data. Okay. Now you like to see, is that true or not? Can you support this claim or not? Okay. Now, first thing that you need to check is the support of your claim is the probability of X and Y. How to compute the probability for X and Y to happen together? You count how many times X and Y occurred together, divided by the total number. So this, for example, happened together. 1, 2. We have 2 cases. If we, let's say, we have 100 input, so this will be 2 over 100. This will be 1 over 50, for example. This is the support. So the probability will be very small in this case. So as the support becomes higher and higher, then this supports your claim. This is the name that support your claim about the situation. Okay. Now, it might happen that this is not because they are related, but X and Y already many times happening in the data. So this can reduce, actually, even the support is high, but it is not good good criteria. So we need to have this confidence for the support. First, we check the support. Second, we check the confidence. What is the confidence? The confidence, it means that X leads to Y is the probability. What is the probability that Y will happen given X has already occurred? What it means that this by Bayesian or by conditional probability is equal to probability of X and Y divided by probability of X. Probability of X and Y is nothing but the support. So we divide this by probability of X. Okay. As we have closer to 1 for the confidence, it means that this support our claim that yes, Y depends on X because this is very close to 1. Okay, so as you becomes closer and closer to 1, then this support your claim. The final thing is the left, or known as the interest. So the interest of the association is given by the probability of X and Y divided by probability of X times probability of Y. We know that if probability of X and Y are independent, this will be probability of X times probability of Y. Okay, so if they are independent, so when you divide them, you will get 1. So if you are very close to 1, then this will reduce your confidence about even if those numbers are high. But if this close to 1, it means that X and Y actually they are independent, but you got high numbers because they are repeated in the data many times. This is the reason that you have close to 1, and here you have high support. But this proves that they are more likely to be independent to each other, so they are not depending to each other. Okay, but if this much larger than 1, then this gives you more support that about your data. If this much less than 1, it indicates that if X happen, then Y most likely will not happen. Okay, so it gives you also the direction of possibility, because not necessarily that when X happen, then Y will happen. So sometimes when X happen, this will prevent Y. So if you are much less than 1, then it gives you that like reverse relation. If it gives much larger than 1, then it gives you indication that when X happen, yes, Y most likely will happen. If you are very close to 1, then it is more indication that X and Y are independent to each other. And actually you can compute any of one from other. So the support divided by the probability of X gives you the confidence, okay? And also the confidence divided by the probability of Y gives you the lift. So it is very easy to compute over data. Even if you have like hundreds of millions of data, you can make this check very fast. So it doesn't take time to check the support and the confidence and the lift. Okay, let us take this example. So assume that you have in database with 100,000 entries. So you use some Python, for example, to compute the confidence and or you count how many X you have and how many Y and how many times X and Y happens together. So you found in the data that X was like occurred or repeated 1,000 times, regardless of anything, just X. For example, this X1, X2, X3, 1, 2, 3, repeated 1,000 times. Okay? And Y equal to 1, so the probability of X1 equal to 1 and X2 equal to 2 and X3 equal to 3, this probability, because it is repeated 1,000 times and we have 100,000 elements, so this probability will be 1,000 divided by 100,000. So this will be like 0.01. This is the probability of X. The probability of Y, so they said that the event Y that you are interested in repeated, the total number of X 1,200. So 1,200. So it will be like yes, 0.12 is 0.12. Yes. And the probability that and Y occurred 1,000 times. So Y occurred 1,000 times. So the probability that Y equal to 1 is equal to, it repeated in the data 1,000 times divided by the total number of data that you have, then you have 0.01. Okay? And then they asked you to check the support and the confidence and the lift. So the support is the probability of X and Y happens together. So actually X and Y happens together was 1,000. So the probability of X and Y together, X and Y, it was 1,000. So it is 1,000 divided by 100,000. So it is 0.01. So in that case, we have 0.01. The support is very small actually. The confidence is the probability of X and Y divided by the probability of X. Okay, so and we know the probability of X, so this was, the confidence was 0.83. So the confidence is very good, close to 1. Okay, and also the left, we divide the confidence by the probability of Y, and it gives 75.8. Okay, what it means, the left is very high, so it is good in that sense. So it supports our idea or our assumption. The confidence also gives us more confidence about this assumption. The only problem that we have here is the support. So the support 0.01. What it means? It means that this assumption is valid for the current data, but we cannot generalize it. So we cannot generalize. We cannot say that it is a fact that once X happen, then Y should happen. Because the support is very small. So you have little data compared with the large database that you have. So that this happens at very small. So you can't here generalize this result. So you cannot claim that it is always general to be in this case. But if, for example, the support was also large, like 0.7 or 0.8, then you can be more confident to generalize this result. We have some exercise. We have data in model. It is called data association.txt. So you can try to read this file by using, for example, Octave or Python, and try to find the rules about this association and association rules to find the claim given in this exercise. Is it good claim or not? Okay. Yeah. Now about the functions of random variables, we continue in the about some basics of probability. When we have random variable, we explained random variables last lecture. So for example, x, then we have some function of x, any function of x, so equal to y. So since x is random variable, then y will be also random variable. So if we know the distribution of x, we can easily also find the distribution of y. This is what is called functions of random variables, and it is given by this formula. Okay. Yes, expectations. Expectations are very important in the probability because usually when we have some uncertainty, that some value which is fluctuating. Okay, so many times we are interested in its mean value or its average value. So the average value, if we have some random variable x which is fluctuating all the time, okay, randomly, or we have high uncertainty, what is the value of x? So the value of x, for example, in stock market, it can be something like that. Okay, so it is some random process going on. So now we are interested to see what is the average of this. So when you say average, you take the expectation. So E of x is nothing but the mean value, the average value. Okay, what is the expected value of EX squared? It means that the average of the squared values, the average of the squared values, okay? And what is the expected value of x minus the mean x all squared? It means that what is the average? Because when you take the mean value, then you now we have the fluctuations. We removed the mean of these fluctuations, so we are looking only for the random part, because we removed the mean, and what is the expected value of this square. So this is called the variance. This is called the variance. So every time you see E, what you got here is not random anymore. So it is deterministic value, indicates unless of course if you have another random variable, then this will be also random variable. But if you're taking the average of a single random variable, then this will be deterministic value. Okay. In general, the expected value of any function of the random variable, it gives you the average of that function over that random variable. So the expected value is very important in order to study the uncertainties in or any uncertain processes. How it is computed? Simply, the expected value of any function j is the summation of j, weighted summation, and it is weighted by the probability of that x. This is in case that you have discrete x. In case that you have continuous x, then you multiply the function j of x that you are looking for to find it is average, multiplied by the probability density function of x. So this is the general way to find it. Just to give simple explanation how it works. Assume that we have in certain course, let's say we have 10 students, okay, 10 students, and the grades of those students was in this way. So we have student like x1, x2, until x10. So the first student, he got 1 and the second student, he got 1 out of 5, the grade, 5, 1, and 2, and maybe 3, and 5, and 0, and 1, and 2, and 2. Okay? So now we have 10 students, and those are the grades of those students. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, if I asked you, we select one student randomly from those 10, what is the probability that this student received grade 1? Okay. So this probability, this student has a grade 1, that the grade equal to 1 is equal to what? 1, 2, 3. So it is 3 over 10. Okay? The probability that the student has a grade 2 is equal to what? 1, 2, 3. Also 3 over 10. And grade 3 is equal to only 1. So it is 1 over 10. And grade 4 is no 1. So it is 0 over 10. And finally, grade 5 is equal to 1, 2, so it is 2 over 10. So this is the grades that you have. Okay. Now, if I asked you, what is the average of those students? What is the average grade? What is the average grade? So the average grade, you take the summation and we divide by the number. So the average grade is 1 plus 5 plus 1 plus 2 plus 3 plus 5 plus 0 plus 1 plus 2 plus 2 divided by 10. This is the average that as we know it from high school. Okay. Let us take the grades together. So we have how many one got grade 1? So we have 3. So it is like 1.
Excuse me.
Yes.
We need to add grade 0.
Hmm?
Grade 0 is not considered.
Here. Yes, but we add it because we have 10 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we should add everyone.
No, but there, I mean.
Yes, you're right. Grade equal to 0, thank you. Equal to 1 over 10, yes, thanks. And now, this is the average, okay? So, if we like now to compute the average, to like split this number, you can see that how many 1 gets grade 0 is 1. So we have like 0 times 1 over 10. Okay, because grade 0, and we have 0 times 1 because it is only 1, plus how many 1 gets grade 1? So we have grade 1, so it is 1 times what? 1,
3.
2, 3. 3 times divided by 10 plus grade 2, 1, 2, 3. So it is grade 2 times 3 times divided by 10 plus grade 4 is 4 times 0 times divided by 10 plus 5 times how many 5? We have 2. 2 divided by 10. So what is this? The grade times probability. The grade times this probability. So it is the same as we have it here. So the expectation is the grade that we have times it is probability. But now we give it in different way. So we explain how it works. So this is the average that we compute the average. So the average actually is nothing but just we multiply the value by its probability of occurring. So it is the probability value. So it is 3 over 10 is the probability to get grade 1. So in other words, the average of the grades equal to the summation of every grade times the probability that you got that grade equal to I, from I equal to 0 up to 5. Okay, so it is, and because it is directly, the grade is the direct, so we can just multiply I in this case. So this is very important actually to understand what is the meaning of expectation. Expectation is taking the averaging over the random variable or the function of the random variable as it is given here. Here for the discrete case and here for the continuous case. The expectations have some general rules. The expectation of any constant, it gives the same constant. expectation of two random variable x and y equal to expectation of x times the expectation of y if and only if x and y are independent. Otherwise, you cannot do that. Otherwise, you cannot do that. If x and y are orthogonal, then the expectation of x times y equal to 0. So you can see that in case that the mean of one of those is 0, then it will be the same as the orthogonality. So this is the reason that they say that independent random variables are orthogonal, but the converse is not necessarily true. Just to give you example that why it is not necessarily true. For example, if you have y1 equal to sine of x and y2 equal to cosine of x. In that case, x is a random variable, and here x is a random variable or random process. I will explain the difference between random variable and random process shortly. But now we have y1 and y2. Both are orthogonal because you know that the sine times cosine are orthogonal functions. So y1 and y2 are orthogonal, but they are dependent. They are dependent to each other because both of them, they are based on the same random variable. So not necessarily that every orthogonal random variables are independent. They can be dependent, okay, and it can be, of course, also independent. But the independent is includes the orthogonality. The random process x and y are called uncorrelated if the expectation or the covariance equal to 0. This is the covariance, x minus mu x times y minus mu y is equal to 0. In this case, we call them uncorrelated. Okay. If we have random process, so the random is like changes with time. So we need to define the autocorrelation function, as we explained later today. That the autocorrelation function of a random process x at two different times t1 and t2 is the expected value of the x at t1 times x at t2. Here we have a few slides that we computed the expected value of some famous like probability distributions or mass function or distribution function, but I will skip all of those. And the t distribution, I just explained shortly what is t distribution before the break. So assume that we like or we are interested to compute the average age where certain person got, for example, diabetes, okay, becomes diabetic. At what age, okay, usually, or what is the average age? So we are interested now in x bar. So our event x or our random variable x is the average age where a person got a diabetes. Okay, now let us that we are in a society that we have maybe let's say 100,000 persons, they have diabetes. Those are the discovered. Maybe that we have also some like thousands. They are not recorded or registered yet as a diabetic people. Okay. Now, of course, we cannot go and check all of them. Maybe they are not recorded. So we have some sample. So we take a sample of 20 persons. Okay, that all of them they have diabetes, and we checked at what age everyone got it. So, and now we compute the average. So the average equal to 1 divided by 20, and the age for every person, maybe the first guy got it at 30, the second guy got it at 70, the third one, he was child, so he got it at 7 years, and so on. So we compute the average. So the average was, let's say, 49 years, for example. Okay? This average actually is the average for the sample, not the average for the population. This average is only average for the sample that you have, 20 persons, but not for the whole population. Okay. Are we interested in this sample or the population? Of course, we are interested in the population, in the original for the data. So because we would like to see at what age usually people they will get this diabetes for those who have the ability or the possibility to get it. So in that case, we are looking for the general or the original average. Okay. We like to build some confidence interval. Confidence based on the data that we have. So we have 49 years old. So how much we are close to the original data, or the original average, or general average, or the parent average. Okay. How can we do that? It is possible to do it with the confidence interval. What is the confidence interval? Confidence interval says that the probability where the like parental average, the general average, or the right, the correct average, to be like greater than or equal to and less than or equal to. So we have some range. So it should be based on the sample that we have. So it is 49 years plus some or minus, actually, because minus some delta, and here 49 years plus some delta. This should be equal to some probability. For example, we say 0.95, for example. Now, we like to build, this is called confidence in probability. Now you have some confidence. For example, if xb bar was less than or equal to 52 years and greater than or equal to, let's say, 47 years, for example, with 95%, so I can say that 95%, I am confident, 95% that the parental average, or the original average, is between 52 years and between 47 years and 52 years, people, they will get this diagram. Okay. How to build this confidence interval? To build this confidence interval, we have to put some assumptions. One assumption that x bar, this one, has Gaussian distribution, is normal distributed. Okay, and this assumption actually is very well accepted or justified, because as from central limit theorem, when you have summation of many random variables, regardless of the distribution of this random variable, so this random variable will be more likely to be normal distribution. So in that sense, this assumption is very well justified. Okay. Now we can compute easily this probability if we know the variance. So if we know the variance of data, it becomes very easy to compute the probability by using Q function, as we explained or we gave last lecture. So or error function, then you can compute this probability. The problem that usually we don't have the variance of the original data, but we can estimate the variance. How to estimate the variance? We can estimate the variance from the data that we have. So we call it in this case S squared equal to 1 divided by n minus 1 summation, and this is the actual data that you have minus the average that you already computed. In that sense, this covariance or this variance is estimated function, and actually this maximum likelihood estimation of the variance itself is a random variable, and it has chi-squared distribution. So in order to find the probability, we need to build this new random variable t, which has Gaussian or normal divided by chi-squared, and this distribution is called t distribution. And based on the t distribution, we can find now this probability more accurately than before. Of course, if you this will be very important if you have a small number of data, like if your data is like 7 or 8 samples or 5 samples, then you need to do this one. But if n is large, if your data already, like in this case 20 or 30, you can assume that it is also Gaussian, and you can do that as a Gaussian distribution or normal distribution as well. So this is the concept of t distribution. Concept of t distribution. Remember, this is the main thing that I want you to know, that in order to find the confidence interval of your inference of data about data. And this is important also in machine learning, as we explain starting from next week. Okay. So here are just some few examples and exercises about how to compute it. If distribution is just, I will skip it, because it is only used when we want to test the fitness of certain random data that we have with some special probability density function. especially when we talk about data clustering in case that we don't have labeling. Okay. Okay, we take a break, 15 minutes, and then we continue. And by the way, after the break, we will talk a little bit about the quiz. We have quiz today, but it will not be in the class. So it will be at home quiz. And the instructor of the course will explain about this after the break. After the break, he will say a few words how to make this second quiz. Thank you. Hello again. So before we start, I just wanted to mention that I uploaded one video about how to use the artificial neural network function that we designed in this course. So it is the video is already in Moodle and also on YouTube. If we completed this lecture before the end of the time, then I can also show you how to do it over Octave here in the class, how to solve some simple problems, and then you can use the same concept in your master thesis, for example, or on the preparation of the report for this course. And before I continue, I just give the word to Rashid to talk about a little bit about the quiz. So you can tell about the quiz today.
Yeah, thank you. The quiz is on now in the module. It's just one attempt for 1 hour. So it starts now, like from Wednesday until Saturday. So just one attempt, but it's mathematical intensive. So not that difficult, but if you read, actually all the questions were taken directly from the materials. It covers part 2 and part 3 of the course material. So if you read the material, then obviously you will be able to answer the question. Thank you.
It is open book, so you can use, of course. It starts from today until Saturday.
Is there a time restriction?
It is 1 hour. Once you open it, it is one attempt. Once you open, then you have to finish within 1 hour. Okay? So don't start when you feel that you have time to do it.
Just 5 questions. 1 question from linear regression, another one from Bayesian and classifier, the third one on the association rule, and the 4th and the 5th are inferences, like deductions from your answers. So those are just 5 questions.
Yes, and if you have questions, you can send email to Rashid to answer. Okay. Joint distribution. A joint distribution here about it is very similar to what we saw about the discrete probabilities, but here we have like continuous case. So here the joint probability density function between 2 random variables x and y is f of x and y is the same, has the same concept that it will be f of y given x multiplied by fx of x, and they will be multiplied together in case that x and y are independent. So it is very similar to the discrete case. Okay, here we actually those slides were given in different course related to digital communication, where we went through very details about the derivations, but for this course it's not needed. However, they are already in the slides, so if you need or if you want, you can study them. So here we gave some examples. Okay. Yes, random process. What is random process? Random process is a random variable, but it is repeated with some independent parameter, for example, with time. If you throw the coin, you get head or tail. This is like a random variable. Or when we give a number for this parameter, like we say head is 1 and tail is 0, for example, once you toss the coin, then you will have a random variable. But if you repeated this tossing every second, then what we have? We have process. It's something continuous. Then we have process. It is a random, but now we have random process, not random variable. So it can be also with distance or with frequency. With any independent parameter, we have a process in that case. If we throw a die. So if we throw a die, then we can have, and our random variable is the number of dots. So we have 2 or 4 or 5 or 1, whatever. So, but here we can see that maybe every second we throw the toss and the die, and then we record the number of dots as we can see them. Okay. Now if we have 4 of them, if we have 4 dice, and we gave those dice, those 4 dice to 4 students, and we ask them, everyone, just to keep throwing it as the time that he wants. For some student, he throws every second. Maybe someone every 2 seconds, someone maybe every 5 seconds, or someone maybe randomly, that every time that he wants to throw it, so he throws it. And now we will have this in symbol. So the in symbol contains of the random variables itself, but we have also time realization. We have time realization. How to study this? Now we need to modify a little bit about the probability theory or the probability concept to add also the time domain. Now we have a random process. If we fix the time at certain time, for example at t1, and we look to the outcomes, we will have just 4 random variables in this case, because we will have like 4 dice, and those the outputs, if the outcome is the number of dots, then in this case we have maybe 1, 1, 1, 1, or 1, 1, 1, 2, until we have 6 4 times. Okay, so now we have all these 6 to the power 4 possibilities at certain time. Now if we just fix the time and look to the outcome, then we have just like this sample space with all possibilities, and every one, of course, it has its own probability to occur. Okay, and of course if we are looking for the average, for example, then the average for this one is 1. The average of this one, that 1 plus 1 plus 1 plus 2 over 4, we can put the average for every outcome. Okay, but this average will be valid at this time. This average will be valid at certain time. If we take another time, t2, we might have different average. So in that sense, the average now becomes function in time. In that sense, the average now becomes random in time. So the expected value of a random process x at time tk is equal to the mean, the average, but this average is valid at that time. When we deal with a random process, then also we can define the autocorrelation function. So the autocorrelation function is the expected value of x at t1 and x at t2. So the autocorrelation is Rxx between 2 times t1 and t2. It gives you the expected value of x at t1 times x at t2. Actually, the autocorrelation function, in that sense, in time process, it indicates the randomness in the signal, how much randomness of the signal. So if the random, for example, if we have autocorrelation function, it has this shape, and we have another one, it has that shape. What is the difference between those two? This autocorrelation function of random x, and this is another one for, let's say this is for x and this is for y. Okay, so we have random process x of t, random process, it is function in time, and this is y of t. Okay. This process, it means that the correlation, the autocorrelation, becomes very small after some time. After some time, let's say lambda, then the autocorrelation becomes very small. What it means? Correlation, it means that how much the data are correlated to each other. Okay? So after some time, the correlation becomes very small. So the randomness in this random variable or random process is more than the randomness in this random process. If this signal, for example, represents, let's say, a stock market, for example, And let us draw how it should be for x and for y. So for x, because it is less correlated, so in that case, x of t can be something like that. Very fast changing, so more randomness. Here indicates that the correlation is high until some time. So if you draw y, you can find something like that. It is random, yes, it's still random, but it changes in this way. So it becomes easier actually to predict if you are at a certain time, you can predict more what will be after some time because it is highly correlated. And this one is highly correlated, this one is less correlated. So the correlation, it gives us some indication to check the randomness in the signal, and also the fast Fourier transform or the Fourier transform of this autocorrelation function. It gives also the post-pocket density, which indicates the frequency content, the average of the frequency contents in the signal. Okay. But both of them will depend on time. I will not go in the details, as I said that it is maybe not important for the machine learning course, but it is important to remember some concepts. When you take the mean at time t1, and you take the mean at time t2, or you take the mean at any time, always the mean is the same. So the mean does not change with time. Okay? And also the autocorrelation, for example, the autocorrelation between t1 and t2, it doesn't matter what is t1 and t2, but it depends on the difference between t1 and t2. In that case, we call this process as a stationary process. Stationary process means that this process doesn't depend on the time itself. Okay, so the mean is the same. So if you take the mean here, or here, or here, wherever you take the mean, always gives the same mean, does not change with time. And also the autocorrelation doesn't depend on at what time you take T1 and T2, but it depends only on the difference between T2 minus T1. In that case, we call this process as a stationary process. It makes the analysis much more easier. Furthermore, there is another case if you take the mean at time t1 or t2, and then you take the mean over one time realization. If you take any of those, one time realization, and you computed the mean for one of them, you find that mean is the same as the mean over the ensemble. In that case, we call it ergodic process. It means that it is enough for you to pick up one of those time realization in order to extract all required statistical properties of the random signal. So in that case, we call it ergodic process. So ergodic process makes the analysis even much more easier. So we have the general random process. A special case, we have stationary random process, and more special case, we have ergodic random process. So to be ergodic must be stationary already. Okay. Yes. The final thing for today is the Markov chains. Actually, there will be one part about hidden Markov models, where we see how machine learning could use the Markov process in order to learn some behavior. But here we just talk very little about the general Markov process, what it means. Okay, let us start with example. It is much easier to start with example. If we assume that the temperature is it can be greater than 0 or less than 0. Okay, so now we have states that either greater than 0 or above 0 or less than 0. If it is above 0, we call x equal to 1. If it is less than 0, then x equal to 0. The temperature in Vasa, is it greater than 0? If it is greater than 0 is 1. If it is less than 0 is 0. Okay, so now how many states we have? We have two states, x and 0. Okay, now we connect to time. So let's say that we talk about days. So x, if we start with x0 here, it means that today. x1 is tomorrow. x2 is after tomorrow, okay? X minus 1 is yesterday, and so on. And we are interested now to see how the process is going. Is it less than 0 or greater than 0? How to process, because now we have time. This is time now, okay? And we have random states for at each time. Okay. One possibility that you assume that they are independent. So it doesn't matter, tomorrow can be greater than 0 or less than 0 independently from today. You can assume that. But this assumption is very strong assumption because it makes it is hard to justify. It is hard. Strong assumption means that bad assumption. That it is quite strong to be believed. Okay? Because you cannot justify this, that tomorrow doesn't depend on today. Or day after tomorrow will not depend on yesterday, and so on. So actually they are depending on each other. Okay? They will be independent if they are uncorrelated. But actually the temperature of tomorrow somehow will depend on the temperature of today. And today depends on yesterday, and so on. How to solve this problem? We can do it by considering the past. But also considering many of past days can complicate the problem. So Markov give very interesting, in between, not independent but not fully dependent. So they said that the probability that for x at time n to be, for example, at state I, in this case we have two states, but we can have any number of states. Given that x at n minus 1 at whatever state, and xn minus 2 at xn minus 3, and so on. This, if you say that this one equal to probability of xn equal to I, this assumption, you assume that they are uncorrelated, so they are independent. Okay? This is, as I said, in many applications, it is bad assumption. Another situation, you say that equal to probability of xn equal to I, and given all these, xn minus 1, xn minus 2, and all, and this will be difficult to solve. In between is Markov. Markov said this one equal to probability of xn equal to I given xn minus 1. So in Markov chains, we considered only the last state. We considered only so the temperature tomorrow depends only on today, not on yesterday, for example. Okay? Like someone going in steps like this one. So the step at any time depends on the step before. Because they will be already correlated. Because for today depends on yesterday. And yesterday depends before day before yesterday, and so on. So it will continue in this way. So this is called Markov chain. Markov chain, that the states at certain time depends on the states on just the previous time. Does not depend on the old history. Okay? And if we take this example of the temperature in Vasa, so we said that if x equal to 1, then at day n, it means that at day n, day number n, the temperature will be, let's say, greater than 0. And if xn equal to 0, it means that at day n, the temperature will be less than or equal to 0. Now, how to study this? We can put, like state 1, we have state 0, and we have state 1. Okay. And in this case, we say that the probability, if you are in state 0, it means that the temperature is less than or equal to 0 for today. What is the probability that tomorrow will be also state 0? This is represented by this probability. So probability from 0 to 0. This is the transition probability that today is less than 0. What is the probability that tomorrow will be less than 0? It is B 0, 0. What is the probability that today is less than 0, but tomorrow is greater than 0? Then this is the probability of 0, 1. What is the probability that if today is greater than 0, what is the probability that tomorrow will be less than 0? This is probability 1, 0. And finally, this probability 1, 1. If it is more than 0 today, the probability tomorrow will be more than 0 is given by this way. So this is very famous for Markov chains. This is very famous for Markov chain. And then we can compute many characteristics from this. Remember that for every state, the total coming out from the state must be 1. So if you are in state 0, so probability of 0, 0 plus probability of 0, 1 must be 1. Because if today is less than 0, okay, you have two options for tomorrow, either less than 0 or greater than 0. So you don't have other option. So in that case, the probability must be 1. And also for this one, so probability 1, 0 plus probability of 1, 1 also must be 1. Okay, we can also build the probability matrix. Probability matrix here equal to B00, B01, and B10 and B11. This is called the probability matrix for this simple case. For example, if we say that based on the history, if you look to the database, you find that when today is 0 is less than 0, the probability that tomorrow will be less than 0 was 0.7. This implies that this will be 0.3. So as I said, that summation must be 1. Okay, and also based on your database, you found that the probability if today is greater than 0, the probability that tomorrow is less than 0 is, let's say, 0.6. It means that this will be 0.4. Okay, what is this? This is the probability matrix, and actually this is what you learned from your data. So you have data, your machine will build this probability. Based on this probability, you can estimate the probability how will be the temperature, let's say, after 5 days. For example, if today is less than 0, okay, today is less than 0, and I asked you, based on this numbers, what is the probability that after 3 days it will be less than 0? Okay, let's just see. Today is less than 0. After 3 days, it means that one option, that 1 day, 2 day, 3 days. So it will be B00 of the power 3. This is one option. Or maybe today is less than 0, tomorrow is greater than 0, after tomorrow is less than 0, okay, and third day is less than 0. So this is another option. So it can be or today is less than 0, okay, but tomorrow will be greater than 0, after tomorrow is again less than 0, and third day becomes the same, less than 0. This is second option. We have another option, plus that today is less than 0, tomorrow is greater than 0, after tomorrow is greater than 0, but in the third day it becomes again to be less than 0. So we have three options now. This is the probability. Okay, this is the probability that on the third day will be less than 0. Okay, how to do that? Of course, this is in two cases. It is easy to find, but in general, this is one of the very powerful tools in this Markov that you can just take. For example, this to the power 3. So if you take the power 3, in case that your Markov chains are all fully connected, this can be, you take that just the power, and then you see this will be that, what is the probability that you will be in state 0 after 3 times. So it becomes that B00, let's say, put it in this way, 3. It doesn't mean that B0 cube directly, but it is computed from here. So you take B of the power 3, then you take the first element here. It means that you are today in state 0, and after 3 days we will be again in the state 0. So it will be computed directly, automatically. So you can see after 100 years, you can take just power 100. So it becomes very easy to find in that case. Actually, Markov chains can be used for many different applications. And it is very nice to be applied in many applications. For example, if one person come to make gambling, okay, and he has, let's say, €100, or let's say he has €50, and then he starts playing with someone, and if he earn €1, okay, or he lose €1. So if he starts with, let's say, with €50, so if he lose €1, so he will go to 49, okay. But if he win, he will get another time 50, okay. But if he lose from 49, he will go to 48. If he win, go to 49, and so on. So it will continue like this one until we assume that if he lost all his money, then the game ended. The game ended. So at the end of the game, if it is 0, then we have here 1. It means that the game is ended. And for example, if he decided that if he earned like 51, okay, the game is ended. So if he play the game, he has 50. But if he received 1, for example, if in the first game he get 51, then the game also is ended. So now we have ended games. The end is died or did end. It is called did end. So it is not going back again to the same. So this also can be modeled, or let's say they okay. You design some game to play with for children, for example, over mobile phone, and then in the game that you make some action to the mobile, and then you see the child taking for example the cursor to be up or down or to the right or to the end based on the action on the screen. Okay, again you can build this as a Markov. For example, depends on the action of the child, how it will be, how it will go. And in that sense, you can make your game to get learn the behavior of the child in order to beat him in the game. So you can build based on many trials, you learn how is the action of the people based on the Markov chain. So most likely, if he got, for example, this red ball in this direction, most likely 70% he will take that action, for example. So you can build also some learning algorithms based on that. Okay. Yes, this is the concept actually of Markov chains, and I gave here some examples how to use Markov to solve some problems. Okay, that's all. I will not cover these points today.